Hello everyone, and thanks for watching Edupedia World videos. In this session of chemical equilibrium, we will look at the topic of degree of dissociation. We'll look at the definition of this term and how to make calculations regarding the same. So let's move on to the definition. So it is defined as the fraction of reactant consumed out of 1 mole of the reactant. Okay. So this means degree of dissociation is always calculated with respect to 1 mole of reactant. So if I had 1 mole of reactant initially with me, how much of it has been consumed in my reaction? So if out of 1 mole, say 0.4 mole is consumed, then degree of dissociation is 0.4. So fraction of reactant consumed out of 1 mole initial quantity. Alright. So it is represented by letter alpha. Okay, the Greek alphabet alpha, and the percentage dissociation is calculated as 100 alpha. Okay, so degree of dissociation is alpha, it is a fraction. Alright, whereas percentage dissociation is simply alpha into 100. The simple way how you calculate any percentage. Okay, multiply by 100. So usually this term percentage dissociation is given in questions. Okay, and even when we calculate, we often report our answers instead of in alpha, we report it in terms of percentage dissociation, that is 100 alpha. Okay, now see, since alpha is a fraction, it is obviously going to lie between 0 and 1. Okay, so alpha will always be greater, or you can say in limiting case equal to 0. Alright, or it will always be less than 1, or in limiting case equal to 1. Okay, so what does this indicate? If alpha is equal to 0, that means amount of reactant consumed is 0. That is, the reaction has not occurred at all. Okay, so alpha 0 means that the reaction is not taking place. Alright, so that is why alpha is always greater or equal to 0. It cannot have negative value, and since alpha is defined out of 1 mole, okay, that is how much fraction is consumed out of 1 mole, so it has to be less than or equal to 1. So if alpha is equal to 1, this indicates that the reaction is completely done with, that is, the reactant has been consumed completely. Okay, so for our cases where we have reversible reactions, okay, the reaction will not go to completion, and hence alpha will always be less than 1. Okay, and it will be greater than 0, assuming that we are studying a reaction which is actually taking place. Alright, so alpha lies between 0 and 1 with limiting values as 0 and 1. Okay, now how do we calculate alpha? Okay, so we have a simple formula. Alpha is simply equal to number of moles of reactant consumed divided by initial moles taken. Alright, so this is how you can calculate alpha for any reactant. Let's take a hypothetical example. Okay, let's say I have HI, okay, which is getting dissociated into H2 and I2. Alright, and this is the balancing which has been given to me. I want to calculate the degree of dissociation of HI at time t. Okay, so first we need to know the initial moles. Say at t is equal to 0, I had A moles of HI and 0 moles of H2 and I2. Okay, now at any time t, I can simply write down that moles of HI are, say, A minus 2x, and moles of H2 and I2 will be x and x. Okay, so we already know how to write in terms of moles. Okay, amounts in terms of moles we have written over here, okay, which we are well versed with. Now how do I calculate alpha? Okay, so see the formula. Alpha is defined as number of moles of reactant consumed divided by initial moles taken. Okay, so that is at any time t, if I want to define the term alpha for this reaction, okay, so the degree of dissociation of my reaction, or the degree of dissociation of my reactant HI, is going to be equal to number of moles of HI consumed. So how much HI has been consumed in the reaction? 2x. So alpha is going to be equal to 2x divided by initial moles taken. Okay, how much quantity of HI did I have initially? A. So 2x divided by A. This is going to be the value of degree of dissociation, okay, with respect to HI, or the degree of dissociation with respect to my reactant, or the degree of dissociation of my reaction. Okay, so what's the use? Okay, one use over here, that instead of writing concentration or moles at any given time t or even at equilibrium in terms of moles directly, that is in terms of A and X, okay, we will now learn how to write the moles in terms of alpha, that is in terms of degree of dissociation. Alright, so alpha is equal to 2x by A. So now simply, okay, calculate the value of x from here. X is equal to A alpha by 2 for this particular example. Okay, and substitute this value of x, okay, over here. So this gives me that at any time t, okay, at the same time t, amount of Hi left with me is A minus 2 into x, which is A alpha by 2. Okay, x is the amount of hydrogen and x is the amount of iodine, that is A alpha by 2. So this means the amount of Hi with me is A minus A alpha. The amount of H2 is A alpha by 2 and the amount of I2 is also A alpha by 2. So here, okay, if I take A common, the actual amount of Hi left with me is A into 1 minus alpha. Okay, and these are the moles or the amounts of H2 and I2. So if you focus over here on the amount of the moles, okay, amount that is in terms of moles of Hi, it is A into 1 minus alpha. So I have replaced A minus 2x, okay, in terms of alpha, and the expression comes out to be this. So look over here, alpha has been subtracted from 1. And how did we define alpha? The amount or the fraction of reactant consumed out of 1 mole. Okay, so this is going to be common everywhere. Okay, for all the examples, alpha is always defined with respect to 1. So it is always going to be 1 minus alpha. Okay, and since initially we didn't have 1 mole of Hi, okay, we didn't actually have 1 mole, we had A moles. So the total amount of Hi is A into 1 minus alpha. Okay, or from here A minus A alpha, that is A is the initial moles, so A alpha has been consumed. Okay, you can also analyze this from unitary method, that alpha is defined with respect to 1. Okay, so out of 1 mole of reactant, alpha has been consumed. Alright, so out of A moles, how much reactant will be consumed? So simply cross multiply. So we get, okay, the amount of reactant consumed is going to be A into alpha. Alright, or you can look at it backwards. Okay, see, if I have Hi going to H2 plus I2, alright, okay, so I know that out of A moles, 2x moles of Hi has been consumed. Okay, so this means if I had A moles of Hi, 2x is getting consumed at time t. So how much of Hi will get consumed if I had 1 mole? That is going to be alpha. Okay, alpha is always the amount consumed with respect to 1 mole. So if A mole leads to consumption of 2x, 1 mole initial amount will lead to consumption of alpha. Okay, and what will alpha be? It will simply be equal to, okay, cross multiply, A into alpha is equal to 2x. So alpha is simply equal to 2x by A. Alright, so this is how we calculate alpha. Okay, number of moles of reactant consumed divided by initial moles taken. Okay, then replace x with alpha, so you can get concentrations in terms of alpha. Over the time with practice, okay, as you replace x in more and more equations, in more and more reactions, you will be able to write directly in terms of alpha instead of writing in terms of x. Okay, so for example, in this reaction, if I wanted to directly write my concentrations in terms of alpha, okay, so let's say initial moles are A, then consumption will always be A into 1 minus alpha. Okay, so if out of A alpha is getting consumed, then H2 form will be A alpha by 2. Okay, that is amount of H2 formed is half of the amount of Hi consumed. Similarly, amount of I2 form is A alpha by 2. Okay, we can look at some more examples in subsequent slides to get a better feel of this concept, but this is an important concept. Okay, even from your competitive exam perspective, like medical exams and JEE mains and JEE advanced, okay, and any other competitive exam where 11-12 syllabus is concerned with, okay, this topic degree of dissociation is pretty important. It constantly comes in the exam and it is also used in different chapters. In fact, in another chapter called ionic equilibrium, we will extensively use this degree of dissociation. That is why we are studying it over here. Okay, though we are not going to use it a lot in chemical equilibrium, it is going to be used later on. Alright, and this is where you should understand this concept. Alright, so let's look at further explanation of alpha. Okay, so if I have some other example, let's say I have N2 plus 3H2, okay, forming twice of ammonia. Okay, it's a reversible reaction and I need to calculate degree of dissociation of this reaction. So how do we calculate degree of dissociation? First we need to define degree of dissociation. Here I have two different reactants, okay, and the initial amounts of them might vary. For example, the initial amount of nitrogen can be A moles and the initial amount of hydrogen can be B. Assuming ammonia is 0 in quantity initially, okay, initial moles are different. Similarly, we know that the amount of any particular reactant consumed, okay, after time t might be different. That is, after time t, okay, amount of nitrogen consumed will only be x, whereas the amount of hydrogen consumed will be 3x. Alright, and the amount of ammonia formed will be 2x. So here the consumptions are x and 3x of reactants and the initial moles are also different. So how do I calculate alpha? Won't I get different value of alpha for different reactants? And if I am getting different values, how do I define one particular value as the degree of dissociation of my complete reaction? It's pretty simple. If you remember the concept of limiting reagent, which we studied in the topic of mole concept, okay, so the degree of dissociation of the whole reaction is always defined with respect to the limiting reagent. Okay, so the concept is absolutely correct that alpha for different reactants might have different values. So degree of dissociation with respect to nitrogen can have a different value from degree of dissociation with respect to hydrogen. But the degree of dissociation of the whole reaction will be equal to the degree of dissociation of the limiting reagent. So you will have to find out which of the two reactants is your limiting reagent. Okay, and the degree of dissociation with respect to that reagent will be the degree of dissociation of your whole reaction. Okay, so for example, let's say in this particular case hydrogen is a limiting reagent. Okay, then alpha will be defined with respect to hydrogen and not nitrogen. You can define another alpha with respect to nitrogen, but then do not call it as the degree of dissociation of the whole reaction. Okay, so if I am defining alpha with respect to hydrogen, then my alpha is moles of hydrogen consumed, which is 3x, divided by initial moles taken, which is B. Alright, so if this is alpha, then my x is simply equal to B alpha by 3. Okay, and I can replace this value of x everywhere to write the concentrations in terms of alpha. Okay, so moles, okay, here we are only talking about moles, not moles per liter. So A minus B alpha by 3, because x is equal to B alpha by 3. Okay, this will obviously be B minus 3 B alpha by 3. Okay, and the amount of ammonia formed is 2 into x, which is this. So once again, if you look at the amount of hydrogen, it is B, okay, B minus B alpha, which is simply equal to B into 1 minus alpha. So for whichever particular constituent you are defining alpha with, okay, so since we have defined here alpha with respect to hydrogen, its moles can always be written as B into 1 minus alpha. That is initial moles of hydrogen into 1 minus alpha. Alright, and then we can write the moles of rest of the reactants or products. So initial moles of nitrogen were A. Alright, so A, how much nitrogen will be consumed? It is always 1:3 ratio. That means always 1/3 of hydrogen. So hydrogen is B alpha. So amount of nitrogen consumed is B alpha by 3. Okay. Similarly, amount of ammonia formed is 2 twice. Okay. That is 2x of nitrogen. So if amount of nitrogen consumed is B alpha by 3, so amount of ammonia formed will be 2 B alpha by 3. Okay, so if you are unable to understand it in these terms, okay, in qualitative terms, in terms of stoichiometry or in terms of unitary method, you can always use this method. Okay, write the alpha value in terms of its definition, then replace the value of x in terms of alpha, and then make your calculations. Okay, alright, if you cannot solve it in qualitative terms or in stoichiometric way. Alright, otherwise always use this method, the direct method. Write the reactant with respect to which alpha has been defined, okay, as this. Alright, and then write the amounts of rest of the reactants and products. Okay, let's solve question based on this concept so that we are sure that we understood the theory and we also know how to apply it in the questions. So let's look at a quick example. Say for this particular reaction where PCl5 is getting dissociated into PCl3 and Cl2, the equilibrium pressure is given as 5 atmosphere, okay, and we have to calculate the Kp value for this reaction, okay, assuming that only 30% of PCl5, okay, was consumed at equilibrium. Right? So what does this term mean? 30% of PCl5. This means that percentage dissociation, percentage alpha, okay, that is percentage dissociation with respect to PCl5 is 30%. Okay, so this value has been given to you as 30%. That is 100 alpha has been given to you as 30. That is to say that alpha has been given to you as 30 by 100 or 0.3, okay, which is always a fraction. So alpha is given to be as 0.3. Alright, so let's see how can we calculate the value of Kp. Okay, let's do one thing. Okay, let's calculate the value of Kp in terms of variables, in terms of total pressure, that is equilibrium pressure P, okay, and the degree of dissociation alpha. Then we will substitute the value of P and alpha. Okay, it will make our solution a bit more complicated, but it will also give you a better understanding, okay, of the concept of alpha and how to use it, and it will also help you to use the same concept, same process in other questions as well. Okay, so instead of directly substituting the values over here, let's solve it in terms of variables. Okay, so our reaction is PCl5 going to PCl3 plus Cl2. Okay, to calculate Kp, we know that Kp is going to be equal to partial pressure of PCl3 at equilibrium into partial pressure of chlorine at equilibrium divided by partial pressure of PCl5 at equilibrium. Right? So given that this is true, okay, given that this definition is true, this way of calculating Kp is true, we simply need to calculate the partial pressures of each of the components at equilibrium. So let's assume that the initial moles of PCl5 were A and the moles of PCl3 and Cl2 were 0 and 0. So this means after time t, I can say that moles of PCl5 left are A minus x and PCl3 and Cl2 are x and x. Let's say this time t is the time at which equilibrium was achieved. Okay, so this means I have the moles at equilibrium. I simply need to write them in terms of alpha. Okay, so how can I do that? Alright, we already know how to do that. So PCl5, okay, PCl3 and Cl2, we know that at equilibrium the moles are A minus x, x and x. Okay, and the alpha value is defined as, okay, moles of PCl5 consumed divided by initial moles taken. So alpha is simply equal to x by A. So this means that amount of PCl5 left with you at equilibrium is A minus x, which can be written as A minus A alpha. X is equal to A alpha from over here, and amount of PCl3 is A alpha, and Cl2 is also A alpha. So these are the moles at equilibrium of all the three components. We have to calculate partial pressures, and if you remember, how do we calculate partial pressures? Partial pressure of PCl5 is going to be equal to moles of PCl5, which is A minus A alpha, divided by total moles into total pressure. Let's say total pressure at equilibrium is P. So total moles, what are total moles? So total moles is simply sum of these three, sum of the three moles, A minus A alpha plus A alpha plus A alpha. So that means total moles is going to be equal to A plus A alpha, which is simply A into 1 plus alpha. Substituting this value over here, we get the partial pressure of PCl5. It is going to be equal to 1 minus alpha by 1 plus alpha into total pressure at equilibrium P. Alright. Similarly, you can calculate partial pressure of PCl3, which is equal to A alpha divided by total moles into total pressure. And likewise, partial pressure of chlorine will also come out to be same as partial pressure of PCl3. So now you have partial pressures of each of the components. You can simply substitute them in the value of Kp, in the expression of Kp, to get your final answer. So your final answer will be alpha divided by 1 plus alpha P whole square. Why whole square? Because one for PCl3 and the other for Cl2, divided by partial pressure of PCl5, which is 1 minus alpha by 1 plus alpha into P. Alright. So this expression will become alpha by 1 minus alpha square into P. So now if you look at the expression of Kp, which we have over here, this will be alpha square. So it will simply be equal to alpha square by 1 minus alpha square into P. That is, it is completely in terms of alpha and total pressure. We know the value of alpha. It is 0.3 as we calculated in the previous slide. So 0.3 square, 1 minus 0.3 square into total pressure. What is pressure at equilibrium? In the question it has been given as 5 atmosphere. So simply substitute this value to get the answer for Kp. Alright. Now once again over here, this method we did was the long method. It looks bit more complicated because we solved everything in terms of variable. To make things simpler, what you could have done was, you could have simply substituted everything in terms of alpha over here itself. Alright, or on the previous slide. You could have calculated the value of alpha as 0.3. From there you could have replaced these expressions. Alright, and then made your calculations. Even that would have given you accurate answer. Another way to do the same thing is, say PCl5 is getting dissociated into PCl3 plus Cl2. Let's assume that initial pressure, that the volume of the container is constant, which means we can directly deal in terms of pressure. So initial pressures of PCl5 is P0, and of these are 0 and 0. So directly writing in terms of alpha, we know that P0 into 1 minus alpha, P0 alpha and P0 alpha. These are going to be the pressures at equilibrium. You can also solve it in this way. If at T is equal to 0, this is the partial pressure of PCl5. At equilibrium, the partial pressures will look like this. This means total pressure is simply sum of all the partial pressures. So it is equal to this. Alright, and which is basically P0 into 1 plus alpha. And this total pressure at equilibrium is given as 5 atmosphere in our question. So from here we can calculate the value of P0. P0 is going to be 5 by 1 plus alpha, and alpha we have already calculated as 0.3, so 5 by 1.3. Okay, and Kp value is simply going to be equal to partial pressure of PCl3 into partial pressure of chlorine divided by partial pressure of PCl5. You know the value of P naught. Okay, alright, P naught we have already calculated over here. Okay, you know the value of alpha as well. Okay, so simply substitute those values to get your final answer. Alright, so even that will give you the correct answer. Okay, by both the methods, okay, you will get the same answer. Alright, so this finishes up the topic of degree of dissociation. And once again, okay, this is not a trivial topic. Okay, though you might not get to use it much in chemical equilibrium, it is going to be extensively used in ionic equilibrium and even in your class 12th and other topics of class 11th. Okay, so until next time, and once again, thanks for watching Edupedia World videos.